Good morning and welcome to the last chapter. We are still dealing with chapter 44, basically from this book. And this actually class 2, and the sequence that you guys are going through, namely the calculus-based class. So we still have to talk about a few items in this chapter. One of them, which is actually an important question, is how do we get into the energies we're talking about? And of course, the obvious answer are accelerators. Some of these accelerators, you have seen them actually in nuclear accelerators, that is. You have seen them in physics too, so we're going to revisit those things to see experimentally how people basically get into the structure of subnuclear matter. We're not talking about atoms anymore. We're not talking about the nucleus anymore. We're not talking even about the protons and neutrons themselves. Actually, we're going well inside of those, okay? And to basically try to see what's inside of those. At this point, in addition to the leptons that I mentioned last time, which are believed to be elementary particles basically on their own, namely an electron, mu1, and also the tau particles, are and their respective neutrinos, because each and every one of them has a neutrino that is associated with it, and also their respective antiparticles, because for the case of the electron, we have the positron, which is an anti-electron. For the case of mu1, you have the anti-mu1, and for the case of the tau particles, you also have the anti-tau particle. And so these are charged particles, so they have their own type particles. And as I mentioned before last time, those are fermions, meaning that they are spin 1/2 particles. Now, the point being in here is that these particles, including of course the neutrinos, are believed to be elementary particles on their own, meaning they don't have constituents inside. That's it. Electron is an electron. There is nothing inside of it. However, we will see that some of the problems that we ran into for the case of the neutron and for the case of the proton is they seem to have properties that can only be explained if they have internal structure, namely particles making them. So hence the hypothesis of the quarks was postulated, and then sure enough, the quarks were actually discovered, but not directly in a sense, because you cannot isolate a quark. You cannot have a quark sitting by itself. So we'll go through the accelerators and basically what it takes to get into those things, trying to discover them. And then we'll also go into now the hadrons, namely the fact that these particles that are made out of quarks, and there are two types. There are the mesons, and there are also the baryons. The baryons are the protons and neutrons that we know of, plus a host of family of other particles, okay? And then you have the mesons, and the hypothesis that Mr. Yukawa proposed in the 1930s, and we will see why that makes sense. And sure enough, in 1947, the first meson, which is a pion actually, or the pi meson, was discovered. And then actually the list of the mesons also grew out of control too. So that is basically where we stand in terms of elementary particles. And then we will see the Higgs also field, how it came to be, because when we try to understand, for example, how electroweak force, the weak force itself, which is the one responsible for radioactivity, for the beta decay, and then you have the strong, the electrostatic force that is mitigated or that is facilitated by the photons. At some point, basically, when we try to raise the temperature, so at some point when the temperature was high enough, these two forces were actually one. Okay, and the model that explains it was proposed by Abdus Salam and also of course, I forgot the other names. Anyway, the point being in here, it was proposed, and later on, sure enough, the unification of these two forces was made possible, but at tremendous temperatures. Okay, and we'll try to understand what that is, but there is a big problem in here, a huge problem. Photons, which are the particles responsible for the electricity and magnetism do not have mass, whereas the particles that are responsible for the weak force do have mass, whether the W plus or the W minus particle or the Z particle. All of these three bosons, they actually have mass, and not just any mass, it's a huge amount of mass, okay? Much larger than that of the proton or neutron. Now, there was a problem now. How can we explain this too? So now the Higgs field was proposed to give rise to the property of mass. So what the Higgs field does is it gives mass to particles. It turns out, with the exception of the neutrino, all of the other particles, they seem to interact with the Higgs field and obtain their mass. So basically, the Higgs boson, which is actually another boson responsible for that oscillations, give rise to the masses of all of the other particles. We have a problem though. Neutrinos, according to the model, the standard model, should not have mass, but actually, experimental evidence indicate that they do have mass, albeit extremely small, but they do have mass, which means that we reached the limitation of the model basically with which we're working. So we know, in other words, we need another theory to go beyond that, explain other things. Obviously, the Higgs boson was a hypothesis that lasted for a long time, and the hunt for the Higgs boson was a big problem in elementary particle physics that required tremendous amount of energy. And sure enough, in 2012 in Switzerland and CERN, that Higgs boson was discovered, which gives rise to which really re-emphasizes the fact that this model is actually a very strong model, and not without its own problems though. But this is the best thing we have at this point. This is the best theory that we have at this point. And it is the most precise theory, and it encompasses everything, with exception that there are two major problems in it. One of them, of course, is the force of gravity that is not anywhere in it, and that's a problem. And the other problem, as I was saying earlier, that this model predicts zero mass for neutrinos, whereas experimental data indicate that neutrinos actually do have mass. So this is basically, in a nutshell, what this whole thing is, and basically where we stand in terms of this model and everything else. We will finish this whole discussion by talking about the universe, basically, a cosmology to be more precise. First of all, try to understand the state of matter right now, where we are in terms of the universe. And we take it from relativity first, and this is general theory of relativity, and try to understand where the universe is based on the current observations, actually, and the data that we have. Of course, we know the universe is expanding, and the further away the galaxies are, the faster they move away from us. And this expansion is happening in all directions of the universe. Okay, so if we happen to be on another galaxy on another side of the universe, we look at the entire universe, and we see our own galaxy, depending on how far we are from it, it's receding from us, indicating what's going on in here is that it's not really the galaxies that are moving. It is the space between them that is stretching. Okay, Mr. Hubble, when he first discovered that in the late 1920s, he was able to measure the rate at which the galaxies are receding from us using basically the redshift that we talked about a long time ago when we discussed the relativity and the Doppler effect. So from that, he was able to determine the rate at which galaxies are receding. Okay, it turns out to be a huge number. I mean, relatively speaking, of course, depending on how far the galaxies are. Some of them are extremely fast moving away from us. If we reverse engineer this idea, basically, we will find that the universe at the beginning was a singularity. What I mean by that is the entire mass of the universe, everything that you can think of, was in a single point in space. And what I mean by that, space did not even exist at that point, okay? So when and where does not make sense, okay? Because the when and the where did not exist. Time did not exist, space did not exist. So at that point, there was basically, as far as we can tell, up to the instant, the moment of 10 to the negative 43 seconds, we have no clue what happened before that, namely from t equal to 0 to about t equal to 10 to the negative 43 seconds, there is no physics that can explain to us what's happened. But we have an idea of what happened at 10 to the negative 43 seconds, and then around 10 to the negative 35 seconds. And then later on, as time evolved, up to about 10 to the power, about 3 seconds later on, after the Big Bang, then we can discuss things based on the energies involved, based on the temperatures, and up to about 380,000 years from the initial, basically, moment. Then we have an idea also what happened, and up to this point. So basically, this is the whole discussion. So we're going to base it on what we know from the elementary particles that we're discussing in chapter 44, and based also on the forces that are involved. So this is basically the extent of which this whole discussion is going to go. Now, where is the universe going to go? That's a good question. Is it going to continue, because now we know it's expanding, is it going to continue expanding indefinitely, basically, at an ever increasing rate? In other words, you come and point in the future, trillions and trillions of years from today, and even the atoms, okay, and the neutrons inside the nucleus starts to recede because the space between them starts to expand. So at that point, there will be nothing, basically. In other words, everything stretched so far away that when you look at, first of all, before that, when you look at the night sky, you will be the only galaxy you will see is our own galaxy, and then at some point the stars also recede from each other, and at some point even the atoms recede from each other at this increasing rate. So that's a possibility. The other possibility is if there is enough force of gravity, it's going to continue, it's going to slow down, and at some point it's going to start to come back again, until it comes back to the singularity again, because the force of gravity will start to bring everything back again until it overcomes all of the other forces, and the universe becomes hot again, and then it's going to restart the whole process again. So that's another possibility. The third possibility is that there is not enough matter in the universe for it to continue, for it to collapse on itself. But there is not enough matter to keep on pushing it away anyway. It's expanding forever at an increasing rate, but just a critical value. We will deduce that critical value. We'll calculate that critical value, okay? And we will see actually that the universe, current density of the universe is actually at that critical value, okay? So actually this is based on observations and calculations and things like that. So this is basically in a nutshell what this whole chapter is. Okay, so again, let's start from what I promised we should start, and namely the nuclear accelerators. Let me find the stuff that you did. Did you guys remember that from physics 2? The cyclotron and the betatron and also the synchrotron. Does this ring a bell to any of you?
I do not remember that at all.
Okay, I think it's at least one of them is a big detailed problem that usually it's in the book actually. Usually assign it as an assignment, but no big deal because we really have to have an understanding of where this data is coming from. Okay, so the first one was a cyclotron, and this was done by Lawrence and Livingston, I think, working together around the 1929, around that time also. So basically, the idea is the following. So what we're trying to do in here, we're trying to accelerate. So we're trying to build accelerators to accelerate these particles to give them high enough velocity. So at some point, we're going to smash them into one another. These are the atomic smashers, they are called sometimes. Okay, and that's the whole point in here. So ultimately, if we give them high enough kinetic energy, they will collide with each other. Once they do, they will reveal what's inside of them. And that's what we're studying right now. We're studying their internal structure. So we want to know exactly how experimentally these things were done. So the nuclear accelerators, the first one that was proposed was a cyclotron. And the cyclotron, the idea behind it is made up of a cylinder. So think of a cylinder like this. a hollow cylinder. So it's a hollow cylinder. And it's metallic also. So it has to be of metal. But then you cut it right in the middle. And you take the two parts and you move them away from each other. So this part in here, this region, is hollow, okay? So there is empty in here, emptiness in here, okay? So this looks like the letter D, so people called it D. So it's made up of two Ds. Okay, each one of them is a D, okay? And now you take this two and you put them inside a big magnetic field, okay? So usually it's a powerful electromagnet where the north is on one side and the south is on the other side. And you have your two Ds in here. They're sitting facing each other, okay? Obviously, this is the side view. Looking at them this way. So the magnetic field in this region of space is pointing from north to south, of course, and it's pointing along these lines. So this is where the magnetic field is. This gap is so small, okay, that whatever the effect of the magnetic field is going to be negligible, okay? So, or if you want to just ignore this, I mean, make sure that the magnetic field, there is no currents in here, so you can wrap the wires in here and skip to the other side, and the same thing, wrap them or the wires, so that when the current runs in here, it's going to create a magnetic field and another magnetic field, and you have the region of space in here. The thing is, by symmetry, you have to have the same magnetic field B, okay? So the intensity of the magnetic field is fixed. And you can dial it up or down depending on how you want, just by making sure that the current that runs in the coils in here is high enough so that I mean, you can control that value, basically. That's the point in here. So you have, usually the magnetic field is around 1 Tesla, okay? Which is a big value, by the way. So you have a strong enough magnetic field in those regions. Now let me go back and look at it at the top view. The top view is going to be helpful for us in this case because it's going to give me a different perspective in here. So what I have in here, I have a D looking from the top, and I have a D from the top. And of course, if I'm looking, this is where the top is. So the top view then, the magnetic field is coming to me, okay? So the magnetic field is pointing outward. So let me draw the magnetic field with the, so the magnetic field in this, the relevant region is inside the Ds. So the magnetic field is pointing upward in here. And it's a fixed value. So it's a static, okay, magnetostatic, not things that are moving in here. So, and the gap between them is actually, we have where we inject in this case a charged particle, an ion, proton, for example, coming from some sort of radioactive materials. Typically, the first experiment was done using a proton. So in here, you have a source of a proton, okay, which is a positively charged, by the way. The Q in this case is equal to exactly E, which is 1.6 10 to the negative 19 coulombs, okay? So they emerge from radioactive materials, and in this case, I have protons. So what do I do in this case? This is what we do. So this is a proton, and I'm going to take to this region and connect it to a battery. So this is the positive region, this is the negative region. Okay, so I have a voltage in here, voltage difference, V, and that voltage difference will cause this proton to move from the higher potential to the lower potential in this case. And that is basically what that is. As a matter of fact, we can find if it started from rest, we can find its kinetic energy by the time it completes this gap, by the time it enters the magnetic field region. And that is 1/2 of mv squared, where m is the mass of that proton, times the velocity it gained. It starts from rest because on average it has no velocity on this side. And it's going to go to equal to the potential energy that is basically lost in this process. It converted to kinetic energy, and the potential energy is exactly E times V, where E is a charge, or Q in general, okay? Let's say it's alpha particle, for example, that although alpha particles are very massive, okay? So the velocity you gain in that case are going to be small. Okay? So you really want to start with light particles like a proton, for example, or even an electron. And you would want to accelerate it. Obviously, if it were an electron, it's going to move in the opposite direction. So the charge in here, I'm taking it positive. If not, then it's going to enter the D2. So this is D1, and this is D2. So for my picture in here, I'm taking a positive charge that's going to go inside D1. Make sense so far, everybody?
Yep.
Okay, so at this point, the particle enters the magnetic region in there. So what we have in there, inside in this region, we have Lorentz force, QV cross B. That should give me the force due to the magnetic field that is acting on that charge, where charge Q now enters with this velocity, given by the square root of QV times 2 divided by the mass, where V is the voltage in here that I have in this region, okay? And that region in here, now this whole entire thing is an equipotential now of voltage, whatever, 0 voltage, for example. So there is no electric field in here because the electric field, there's the potential is constant, and the derivative of a constant, remember that E is equal to minus grad of V. Okay, usually this is the grad, but I'm going to, because I'm taking only one direction, normally E is equal to minus grad of V. But because V is constant in here, so there is no electric field inside. So there is no electrostatic force, because remember the electrostatic force is QE. Because E is 0, then there is no electricity in here. And what causes this one to accelerate is actually the electrostatic force. In other words, there is an electric potential in here pointing, electric field pointing this way. So that is what the E field, that is the one that accelerates this particle and gives it that velocity at the end of the cycle, okay? And the gap, but inside the D's, there is no, the potential is constant. So at that point, there is no electric field. But the charge now is inside the magnetic field that has this effect. So what I have in this case, the force is going to my, according to the picture, is going to my left. The magnetic field is coming upward, okay? It's coming out of the screen. So the force in this case, according to the right-hand rule, is going to be pointing down, and the force changes the direction of the changes the direction in such a way that this particle now is subject to a force that is perpendicular to the velocity. Because if I apply Newton's laws, this must be equal to mdv over dt, and the acceleration is perpendicular to the velocity, and that is the circular motion. And I guess you guys did the effects of the force in this case of the magnetic field on a point charge in physics too, I'm sure. Okay, so this is actually the velocity is tangential. In this case, it's tangential, and the force is perpendicular, so it tends to give it a rotation. So it's going to rotate. So in this case, if I apply Newton's laws of motion, this is going to be QVB, because V and B are perpendicular. Remember, V is actually inside the screen, the way I drew it, and B is coming out of the screen. So they're perpendicular to one another. So sine of 90 degrees is 1. And then this must be equal to m times the acceleration. In this case, the acceleration is v squared over r, because of the fact that I have a circular motion. Because it's the only thing that this force does is change the direction of the charged particle that comes in. So it's going to go through a semicircle and come out. Okay, that's the point in here. And the radius of the semicircle, or the radius of the circle, if it were inside completely, is going to be given by this expression, cancel the v from both sides, and I'm going to have QB equals to mv over r. meaning I can find what that radius is. That radius is going to be exactly mv over qb. mv is actually the momentum over qb. So it's the momentum over qb, basically. That's the radius of this motion. Now, when it comes out, the charged particle is going to find a potential that is not favorable to its acceleration. So what I do in this case, I flip the sign. So I take another potential where this is positive and this is negative with the same V, by the way. Okay. The minute the particle emerges from that, we flip the signal. Okay. So what happened at that point, the particle now will accelerate down this way, because the electric field now points in the opposite direction. Once we flip the potential, the voltage. So in this case, it's going to come out, and when it comes out, it's going to come out on the other side. Its velocity now, I have to label stuff, okay? So this is the first run. So I'm going to call this one 1. And QV is constant, so I can monkey around with those things. And this is actually R1 because the potential that, the momentum that I come in with is the velocity V1. So that's really the expression in here. Everything else is the same. The particle did not change mass. Q did not change, the charge did not change, the magnetic field did not change. So I really have to label these things, because now it comes up with a higher velocity that is given by the conservation of energy 1/2 of mv2 squared minus 1/2 of mv1 squared is equal to the same QV. So the second time around, when it runs through this potential, if I flip it in time, is going to be the change in kinetic energy. Remember, it emerged with the same velocity. The magnetic field does not change the velocity, it changes direction only. So when it comes out, it's going to have a new velocity by the time it enters the second D. So if I use the same math, I will find now the new radius is going to be slightly bigger, because if I use this expression to find what V2 is going to be equal to the square root of V1 squared, when I divide everything by M and multiply by 2, and then plus this term, which is Q times 2 times V divided by M. So in other words, this is basically the second velocity as I emerge with. If I plug in the value of V1, then it's going to give me that term twice, okay? But that's R2 now, because V2 is higher, is going to be even higher. So it's going to be mv2 over qb. So the second time, it's going to run in here, but which direction? It's important to see which way it's coming. So again, now it's moving in the opposite direction. Earlier it was going this way. Now it's going to go this way. The magnetic field is still coming out. So it's like this, okay? I really have to twist my hand, okay? So the particle is moving this way. The magnetic field is still coming out of the screen, and the particle will point upward now, okay? So that's the point in here. So it's going to turn in the other direction. So the point in here is that it's going to emerge with a little higher radius than the first one, and it's going to emerge, and the radius, you can find it from this expression, and it's going to emerge in the opposite direction. So it's going to come out, and it's going to come out with V2, and if I switch the voltage in time, the minute the particle emerges, I switch the voltage, again, back to the way it was in the first time. This particle will also accelerate, will gain more velocity. By the time it enters in here, it's going to have V3. And that V3 is going to be given with a similar expression to this one, except I will have V2 in here, squared. And this quantity doesn't change. And it's going to come out in here. Then it's going to go through a bigger radius now than the first two, because the velocity has increased, and it's going to come out and it's going to go around. Each time it goes through between the gaps of the D's, I change the voltage just enough so that at the end of the day, it's going to gain velocity. So that's the trick by it. At the end, when it completes so many rotations inside, it's going to have tremendous velocity because of this. Each time it goes between the gap, its velocity is going to increase. So at the end, I will have a huge velocity that this particle will emerge off of it. Does this make sense to you guys? The process?
Yeah.
Okay, here is a question. Thank you. Here is a question. What is the rate at which I need to flip this voltage? That's a big question. And the rate of which I need to flip that one is the rate when this thing comes out. So if it goes around the circle using this condition in here, because remember, if I go around the circle once, that's a period t, okay, for a rotation. And the period t is related to the path in here that I take and the velocity. I know the velocity with which we're entering those regions is v. And I know the path in here, it's 2 pi r. So this period t is given by 2 pi r divided by where the r in each case depends on that path. So for the case of R1 is going to be R1, for the case of R2 it's going to be R2, and so on and so forth. But each time I'm coming with a different velocity to describe those paths. So it's divided by that velocity. So distance divided by velocity give me the period t. If I take the inverse of that one, that is going to be the frequency actually with which we need to change the signal, which is v over 2 pi r. Okay, well, omega is equal to 2 pi f. So the signal must have to have this frequency omega equal to 2 pi f. We'll cancel the 2 pi from both sides. It's going to be v over r. If I calculate v over r from this expression, it's independent of v and r, because from this expression, that gives me actually the ratio of v over r. So omega, the frequency then, the angular frequency, which is v over r, must be equal, according to this expression, qb over m. Well, this does not depend on when we run through any of these d's. This is independent of v and independent of r in the same time. So all I have to do then is put an alternating current in here with that frequency. And each time the particle emerges from this one is going to flip on its own, as long as I make sure that the signal has this frequency. So this is called the cyclotron frequency. If I'm doing this correctly and the signal is working correctly, this is going to operate on its own. It's going, you put a particle in here and it's going to run through this one several times. And if you do the calculation correct, you know exactly where it's going to emerge from this d's. So you smash it against, or it comes out on the other side. Maybe it will come out in here. Okay. And you will have your target in here. And you're good. Okay. So this is basically what's going on in here for the case of the cyclotron. The problem with the cyclotron is there are some limitations. One of them, there are two of them, but the second one is secondary to the first one. The first one is that you are running into is that the velocity starts to increase until this expression becomes no good, because then you have to introduce relativistic corrections. Relativistic corrections. In other words, this expression here that I was writing for the radii r is not going, it's going to be the momentum divided by qb. The radius is going to be the momentum divided by qb. And the simplest version of the momentum in relativity is gamma mv over qb, where gamma is Lorentz factor, which is 1 over square root of 1 minus v squared over c squared. So when the velocity becomes too big, when, in other words, when you're accelerating and becoming excited about it, you will find that there is a problem. And I will tell you where that problem is. That expression of omega, which is really mv, which is really has to do with the velocity in here. Where is the frequency? We use this expression to find what the ratio of v over r is. So again, the ratio of v over r from this expression, clearly v over r is going to be equal to qb over gamma m. In other words, this is equal to qb over m, where m is the mass of that particle times 1 minus v squared over c squared. In other words, here is a problem. The frequency decreases and depends on v. And depends on v. And your device becomes unreliable at this point. Why? Because it's not going to change in time. There is a lag. So instead of accelerating the particle, the signal will not change enough for it. So it's going to emerge and find the electric potential pointing in the wrong direction. So it's going to slow down. So by the time it changes, probably it's midway or almost at the end. So it's really slowing it down at some point in here for the higher velocities. So it's going to go out of sync. At high velocities because of relativistic corrections. So this is the problem that you're in. As long as you're doing small velocities, then you're fine, okay? You're going to be able to do this one, but for high energies, this is no good. You can't really work with this one. So what people did then, they proposed the synchrotron, which is really the same device, except omega now need to be adjusted for this correction, okay? So omega variable. When you do that, then in this case, you're taking the minute it emerges, the signal still flips and the particle can be accelerated. So if you have somehow a device that can synchronize itself with the ever increasing velocities, even for the small ones, because this correction is in there all the time, so that the omega is tuning down as the velocity is increased, going down and down, waiting basically for the particle, the minute it emerges, it's going to accelerate it, then you're in good shape. So that's what the idea behind the synchrotron is. So these devices are good, except that there is a problem now, another problem. Or limitations, if you will, not a problem. And the limitation now has to do with the Larmor radiation. Namely, this is a charged particle. And a charged particle will start to radiate energy the minute it's accelerated. And it's accelerated in two places. It's accelerated in this gap, so it's going to lose energy to that. And then also it's accelerating inside the magnetic field, albeit it's not a change in velocity, it's change in direction of the velocity. It's still acceleration nonetheless. So that also loses energy. So now there is a limitation on how much velocity you can achieve with this one in here, and that is because of this radiation of energy. But if you have an abundant amount of energy in here, you can still theoretically achieve whatever velocity you have. Which brings me to the last device that we're talking about in here, and that is the Betatron. And all of this, by the way, are supposed to be in physics too. I know probably you may have a short discussion on them, but they're important for our discussion now, because we're talking about inside elementary particles, and the obvious question is, how do we get into those? How do we get into those structures? Okay, so the Betatron, the idea behind it is actually a little different. So what you have in this case, you have a region of magnetic field. Actually, the shape is not symmetrical. Okay. Even if it's symmetrical, you can play with something else. Okay. So this is actually an electromagnet, and it has to be an electromagnet. Theoretically, electromagnet. The case of the synchrotron and cyclotron and the synchrotron, both of them, you can do them actually with a permanent magnet. But which permanent magnet can give you 1 Tesla? That is a big question. That's why even there we use electromagnets. But in here, we really have to use an electromagnet because B is time dependent. The magnetic field must be time dependent to take advantage of the force that you guys learned about from physics 2, namely that the EMF is equal to minus d phi of the magnetic field divided by dt, namely Faraday-Lenz law. Okay, but there is an EMF that is generated, and it's this EMF now that is going to accelerate the particle if the magnetic field is high enough. And the EMF is just basically another voltage. It's a battery, really. That's what it is. So in this case, you have a torus. I'm going to draw the two ends of it in here. So from the top view, it looks like this. Like a donut, okay? Okay. How many? Is that how you spell donut? I think that's not how you spell it. Okay. Sorry about that. Okay. Anyway, the point being here is I don't eat donuts, so I have no idea how they work. Much easier to say torus. Anyway. So you have a point in here of injections. First of all, you need an injection And again, since it's called a betatron, it has to do with beta particles. Okay. And then here the ejection of this particle, because you want them to come out. And as they come out, usually there is an angle with which they are injected and also extracted. When they come out, you want them to, there is a target again. So you would want them to accelerate. You would want them to have high velocity in here. And beta particles, namely the electrons, are the ones that are used actually to probe inside the neutron, inside the proton, and all of these things. Okay, they're the ones that can interact with those ones, because you would want them to go straight inside and start interacting with the constituents. You're not going to smash a proton against a proton and expect something to go inside of any one of them. So again, this is the cut from it. So you have a region in here of a magnetic field that changes with time. That's the point in here. So this is a time dependent. It starts from negative value, if you wish, and starts to increase up to a certain value. So there is a value for the magnetic field in this region called the tangential region. So this is BT in this region. And there is a value of an average value for the magnetic field, B average, okay? Both the average is changing and the tangential value is changing because B itself is changing, okay? So in this region in here, where the particle is, it's inside a magnetic field that changes with time. So the flux changes in that region. And again, the particle now starts to accelerate, okay? Starts to accelerate because of this EMF. And the acceleration is given, or the force in this case is given by the charge, which is an electron in this case times E times E, where E is the electric field that is created by this changing EMF, okay? The EMF in this case. Anyway, so the point in here, we have a value that we can compute for that force, and that force causes now the particle to move around. But then, if the magnetic field is not really changing and it's given ratio, we have a problem, okay? The same magnetic field is also used to keep the particle in that region. So the magnetic field is forcing the particle to stay in the circle, and the flux of the magnetic field is accelerating it. Again, the circle is given by this expression too. R is equal to momentum of the particle divided by the charge in this case times the magnetic field in this case, okay? So we're going to find the radius, and we're going to force the radius to be equal to the radius of the donut itself. And from that point on, we're going to make sure it stays as is. So we don't want it to change. Well, the condition for that is so that the tangential value, I mean, the calculation is a little bit longer, but it's going to give you this condition. As long as you maintain tangential value for the magnetic field that is half the average of the magnetic field all around, then you can increase it as you wish. The particle is confined in that torus. It's going to stay in that radius, and it's going to gain velocity as you go. And again, the only limitations is the same limitation on the cyclotron, namely radiation of energy. This is actually a very, very powerful accelerator, and you also can reach extreme high velocities for the electrons, which then you can smash them with the targets. Make sense?
Yes.
Okay, very good. So now we have an idea of these so-called atomic smashers. Actually, they are subatomic, they are nuclear. They go inside the nucleus. And let's continue our discussion on the types of particles now. First of all, Mr. Yukawa proposed the following. He said, look, obviously inside the nucleus, there's something going on in here because there's this strong force, of course, that is binding the proton and the neutron in the case, for example, even the simplest isotope of hydrogen, namely deuterium. So this force must be due to some exchange of particles, just similar to the case, for example, of the electromagnetic field that was later on when we discovered the photon. Then we believe that, okay, the theory that was emerging actually around that same time is that the exchange of the photon between the charges, charge 1 and charge 2, namely during the Coulomb force, for example, they're attracting or repelling one another, is the one that is really responsible for their interaction. So it's the exchange of the photon. So similar to the following, to another example, the textbook example is two skaters, for example, on a frictionless surface. In order to maintain the force between them, the distance between them, they have to always be exchanging a ball. Okay, so if you throw the ball at the other one, obviously, and you would want to maintain the distance, because remember the proton neutron, they are at a distance of about 1 femtometer. That is the attraction for the nuclear force. So you'd want to maintain that for that velocity. The ball is coming to you, and if you stay in your place, the ball hits you, so you're moved back. So the distance increases in here. So it's not 1 femtometer anymore. So what you do, the receiver in this case has to move closer to cancel the momentum of the incoming particle. And when it does, then it's going to stay at 1 meter. Then you throw back, then the other person will catch it, and so on and so forth. So it's really a catch of the ball. It's like a game basically between them. So he proposed that that particle has to have a mass of about, has to have a mass, turns out, and we're going to see the calculations in here, of about 220, 230, the mass of the electron. Okay, so let's see here his reasoning for it. Let me share. And he called it actually the meson. So the particles inside the nucleus exchange mesons. So this is Mr. Yukawa's proposal. The meson hypothesis again. So you have a proton and you have a proton, and the distance between them is 1 femtometer. Okay, and these two particles, namely proton and neutron, you don't have to. So in this case, the distance between them is about 1 femtometer. So they must be exchanging a particle between each other. So you send it, the other one catches it, and then send it back, and so on and so forth. And this exchange of that particle, as long as they maintain that exchange, they're in good shape. They are going to maintain that 1 femtometer distance. So the question is, what is the mass of that particle? Okay, or the energy of that particle? Because remember, the energy is simply just that mass times c squared. That's what they're exchanging. So this is the mass of the meson that was suggested there. So they're exchanging that particle, and that is expression of that strong nuclear force. So he reasoned the following. The distance is about 1 femtometer, which is 10 to the negative 15 meters. Okay, between them. That is what the nuclear force was. Now this distance, these particles must be traveling so fast at those short distances that for all practical purposes, we're going to say their velocity is very close from C or C, put it C, okay? So the exchange of this particle must happen at the time scale T, or delta T in this case, that is of the order of distance divided by speed. Remember, the distance is 1 femtometer and the speed is c. So this distance is 10 to the negative 15. This time scale is 10 to the negative 15 divided by 3 times 10 to the power 8 meter per second. So we're talking about 10 to the negative 23 seconds times a third. So it's going to be 3 times 10 to the negative 24 seconds. So this is basically the time scale we're talking about in here, okay? I mean, the time scale, yes. Since we know of the Heisenberg uncertainty principle, he theorized that the change of this mass times delta T must be at least equal to h bar over 2. This is the condition from Heisenberg. Okay. Obviously, I forgot to mention that this whole thing was inspired by the ever-evolving at that point QED, quantum electrodynamics, which was describing how the electron, proton interact by exchange of virtual particles in this case, which are called photons, okay? So this must be a virtual particle, also called the meson, that has specific mass in this case. So the interaction in here between these particles is the exchange of that one. So this is basically the idea behind it. So it's trying to simulate what was going on in QED, which turned out to be a very powerful theory at that point, quantum electrodynamics, to describe the interactions of basically electricity on the quantum level. And that is the QED. That is actually the foundation of the QFT that emerged everywhere as quantum field theory that we're going to be exploring more. I mean, this is the same stuff, okay? It's building on this idea. So now, you wanted to find how much energy we're talking about in here. So the delta E in this case must be of at least, so we're going to talk about orders of magnitude, h bar over 2 times this time scale, which is about 3 times 10 to the power negative 24. So if you put everything in here, this delta E is going to be of the order of h bar. Remember, h bar is 1.055, which is 1 times 10 to the negative 34, divided by 6 times 10 to the negative 24. And 6 times 10 to the negative 24, this is about 1 or 10. Okay, so I'm just going to look for the order of magnitude only. So this is 10 to the negative 24, 10 to the negative, that's 10 to the negative 10, divided by 10, which is roughly a negative 10 to the negative 9. Okay. Obviously, this is in joules. So this is in joules, okay? And how much mass that is in electron volts? Remember, 10 to the negative 19 is electron volts, okay? So 1 joule, I mean, one electron volt is 10 to the negative 19 joules, okay? So obviously we can convert this one to joules. And as a matter of fact, we can write it in megajoules already, 10 to the negative 13. Sorry. Yes, 10 to the negative 13. So 1 MeV is 10 to the negative 13 joules. Okay, just by multiplying by 10 to the power 6. So 10 to the negative 13 joules in mega electron volts. So this is giving me a bigger number than what I was thinking. It should be much less than this one. Did I make a mistake somewhere in my analysis in here? 10 to the negative 15 meters divided by 10 to the negative 8. Yeah, that's about 10 to the negative 24. And in here, H, 10 to the negative 34 divided by 10 to the negative, that's 10 to the negative 10 joules, 10 to the negative 9 joules, which is about 10 to the negative. Well, it's giving me more than, it's giving me about a giga electron volt, and that is way more than what I need in here, okay? So I need to come back to this one in here. Okay, please check the numbers also, okay? So the point being in here is that the mass that he found for this particle is actually only about 230 times the mass of the electron. Remember, the mass of the electron is 0.511 mega electron volts, okay? And this number is clearly coming out to be much, much bigger than what I want to see, okay? So this number, for some reason, 10 to the negative 13 and 10 to the negative 5 is giving me about 10 to the power 4 mega electron volt. And that's more than what I need, okay? So I really need to fix this problem. So we need to check it. I need to check it, okay? And please check it with me too, okay? Make sense? You guys understand what we're supposed to do here? Yep. We're supposed to use the Heisenberg's uncertainty and find an estimate for this mass. Yes?
Yep.
Yep.
Very good. So the point being in here is that he found the mass to be about 220, 230 times the mass of the electron. He did not, a year later, the mu1 was discovered. And people thought that, hey, this is the particle. Well, it turns out to have the wrong charge, because this one should not have a charge. Okay, this particle should not have a charge. The mu1 has a charge, And that was a problem. Okay, it was discovered part of the cosmic radiation that hits the atmosphere. So the muon is not it. And it's not just that, it has the wrong mass, it has all kinds of other properties that are not the same. Until in 1947, where the pion was discovered. And that was actually the first meson. Okay. Then after that, it turns out that there are actually, the pion 0, and then there is actually charged versions of it. And there are a bunch of other particles that emerged later on. Okay. So this seems to work. This seems to fit the bill, okay, in terms of this one's in here. However, there was a problem, as I was saying before. One of them is the neutron. Neutron has a charge that is equal to 0, but a spin that is not equal to 0. It's 1/2, okay? So in this case, when I say 0, I mean 0 times 1.6 times 10 to the negative 19. When I say S equal to 1/2, I really mean 1/2 of an h bar, because those are the units for the angular momentum, okay? So it was a fermion. So how in the world we're going to have a spin which is somehow which somehow has a magnetic moment in this case that is related to this value? Remember, it's value times the nuclear magneton, and it behaves as if it is actually a. So this is the magnetic moment. And in experiments, when you put it inside a magnetic field, it deviates just like the electrons, behaves as if it has a negative charge, distribution of negative charge somehow, and like the protons, which deviate in the opposite direction. So that was a puzzle, and that's one thing. And then the other thing, which started to happen every which way as the energy starts to get higher and higher in those accelerators. Well, it's not just these particles that were discovered. The number of particles starts to grow exponentially, grow very large. Over 100 particles were discovered. And that was a puzzle. I mean, all of these are elementary particles that have been discovered. The lambda particle, all kinds of particles that started to fill the. It was dubbed the particle zoo. Okay. As a matter of fact, one of the, I forgot who it was, during his acceptance speech for the Nobel Prize, he said that it should be now instituted as a law that any person who discovered, because if you want to go and get your PhD degree and you discover a new elementary particle, well, that qualifies, and so that you get your PhD degree and you celebrate and you move on to other research areas, or you continue with elementary particle physics. But then, because they were discovered almost on a regular basis in cloud chambers everywhere, you just follow the where the particle is bending, and then from there you'll find a new particle with different properties, electricity, magnetism, and spin, and then other property that emerged now at that point, namely the strange property, which has also the symbol S, not to be confused with the spin. So this property, which is also quantum mechanical property, is conserved in all of the other processes except in the case of weak force. So weak force seemed to violate this new property that was dubbed strange, and it was dubbed strange because of this region. So you have all of these quantum numbers that are supposed to be conserved, and new particles that have this one. The neutron and the proton do not have a strange value. Their strange value S is equal to 0. And to a point that, as I was saying, he was talking in there now, it should be, instead of rewarding people discovering new elementary particles, they should be fined $10,000 for every new particle they discover, okay? Because there are too many of them, okay? So that really started to have people think, and one of them was Murray Gell-Mann, who proposed the following, that maybe these things are made up of tinier particles, okay? He called them quarks. In quarks, because of the fact that we know the charge of the proton, we know the charge of the electron, we know their spins, I mean the proton and the neutron, we know their spins, we know all of the values related to them, and then this property of the strangeness. So at that point, he proposed three kinds of quarks, okay? And for lack of better words, he called them the up quark, the down quark, and the strange quark, okay? So you have U, D, and S, okay? So there were 3 of them at the beginning. And this, they must constitute, they have to have the right properties so that they give you all the different numbers. So for example, for the up quark, it must have a charge of 2/3. So the Q is equal times E, of course, everything else is times E. So this is a 2/3 of an E, and this is a 1/3 of an E. And this one has to have a charge also. Okay, let me guess it. I mean, I can't remember them. And I don't blame you if you don't remember them because there are too many. Okay. So the strange quark in this case is a negative 1/3 also. I'm sorry, this is a negative 1/3. And this is a negative 1/3. Okay. So if I take the proton has a positive charge of E. Okay. So what I need from this one is 2/3 of an E and another 2/3 of an E, and subtract from it 1/3 of an E. So that gives me 4 minus 1. So it's going to be 3/3. So it's going to be exactly an E as I want to. So in this case, I need to have for the proton an up quark and an up quark and a down quark. Okay, their spin is all of them 1/2. They are fermions. But in this case, this is 1/2 up and this is 1/2 down, and this is 1/2 up, or it doesn't matter. So there is an exchange. So 2 of them must have up and 1 of them has to have down to cancel the other one, so that at the end of the day, I will have a spin that is equal to 1/2 of an integer. Okay. So in this case, so that fits the bill. Okay. So in terms of strangeness, so again, as I was trying to say, please do not confuse these 2 S's. This is a spin. This is a new property now called strangeness. So in terms of strangeness, this is 0, and this is 1. Okay. So now they have other things to worry about. Now, in terms of the neutron, well, this one has a charge of 0. So the way I can make 0 out of these numbers is 2/3 minus 1/3 minus 1/3. That should give me a charge of 0. But there is now distribution of charge between these 2 quarks that are negative, trying to jockey for position with this positively charged quark. But then as they do, they give you that distribution that gives you that magnetic moment. Still, the net charge in this case is 0. So, but then it's an up quark, down quark, and a down quark. Okay. So this explains this too. And if you look at the table now, on page 44.3, it gives you, so, okay, in anticipation of what comes next, of course, there are 3 more quarks that were postulated and actually shown to fit the bill. Okay, the opposite to the, because they need to be in pairs, actually, the opposite to the strange quark is the charm quark. So again, now you're asking, what does this name mean? They don't mean a thing. It's just basically distinction between them. So an up and down doesn't mean that one of them is on top, and so it doesn't mean anything of that. As a matter of fact, you have the top and the down quark. So now you have 2 more. No, not the down. So what am I calling? Up and down, up, top, and the bottom. Bottom. So each one of this is a quantum number that needs to be conserved in one of those collisions that I was talking about, the nuclear reactions that are, so this is the B. So now this completes the picture. In addition to those, you have their anti-associated quarks. So you have the anti-up, which is U bar. So everything that is anti, you just add to it a bar on top of it. an S bar, a C bar, which is the charm quark, and a T bar, and a B bar. Okay. So those are 6 times 2, 12 quarks. Okay. That seem to fit the bill in terms of describing all of this called hadrons. I mean, baryons. These are the super heavy elementary particles. Namely, a proton and neutron are one of them. But if you look at the table in there, the baryons are not that. There is a lambda naught particle. This has a charge of 0. So whatever I need to combine in here, I have to get 0 out of all of these numbers. So the lambda naught particle is UDS. Again, if I look at the chart, U is 2/3, D is 1/3, and S is actually negative 1/3 also. So that still gives me a charge of 0. So hence I have a charge of 0. But now the strangeness is not 0. Okay, so this has a strangeness that is not equal to 0. It's actually equal to -1. Okay. Did I give you the value? Okay, this value is -1 actually. So it's the entire particle that has strangeness that is equal to 1. Anyway, if you look at the entire table in here, it's divided into 2 classes. So you have the baryons that are made up of 3 quarks, all of them. Okay, and that's the second part of that table. And it gives you their masses, and it gives you their charges also, and it gives you their spin. All the baryons are fermions. Okay, the spin for the most time is for the most part is equal to 1/2, but even 3/2 also are fermions. Okay, and then it gives you their baryon number. So all of this must have a baryon number that is equal to 1. So B, capital B, is equal to 1 for the baryon numbers. And this is also must be conserved in any nuclear reaction. So you start with such a number of baryon numbers. It doesn't matter which particle you start with. If you start with a proton, neutron, it doesn't matter which one of these particles, or a C particle, which is another particle that is important in this case that we probably want to explore. Okay, I think this is the symbol for the Xi. I don't know, I call it Xi, but probably some of you might hear it as, is it Xi? Okay, is that how you say it? It's the Greek letter that they say Xi. Anyway, this is another particle that comes up also in different charges. Okay, negative and 0 and negative. So all of this have a baryon number that is equal to 1. In addition to that, you have the mesons. So the mesons baryon number is 0. Mesons, the ones that we talked about, one of them are the pions. They're made up of 2 quarks only. Okay, a quark and an antiquark. Okay, so this is Q in here is a symbol for any of those quarks, okay, any of those family of quarks. But in this case, they always come into 2 different kinds. They come in a quark and antiquark in this case. So their spin is going to be 0, and their baryon number is 0. But some of them have a strangeness. Okay, some of them have a strangeness, and those are the kaons. So the 2 particles K plus and K minus have strangeness value that is not equal to 0. And that's actually how the stereo strangeness property was discovered. Okay, it was discovered when we started discovering these kaons that have this strange behavior, and that's how the property was named from there. And then the hypothesis for the quark also that is associated with it. Okay, so again, it gives you the mean lifetime and which way they decay and what form they do. Okay, I want you guys to look at that table because a lot of the problems from the end of the book are related to that table. In addition to the 2 tables that I mentioned before, 44.2 for the leptons, and also to some extent 44.1, and that just gives you basically the masses, for example, of the W plus and minus and the Z bosons, which are important in this case. Now, everything looks beautiful. Everything is, at this point, looks fine and great. The only problem with it is, as I was saying in here, is the gravity is not part of the picture. Okay. You do calculations based on this model. There is one thing in here that I need to mention, and that is the colors. Okay. Now that's a property, okay, again, so it's just called color, not to be confused with actual color, not actual color. And again, just because we want to understand the interaction of these colors, so we came up with something called QCD, quantum chromodynamics. So what quantum chromodynamics is, appends another property to each one of those quarks and gives it that property, that specific value. Later on, they called it color. Okay, so you have the blue color, you have the green color, and you have the red color. Okay, just like the RGB, the colors on the and light. Okay, because we noted that this property, they mix only according to certain rules, as if. Okay, the math is way beyond the scope of this one. As a matter of fact, if you look at the Lagrangian for this theory in here, it's ridiculously long. Okay, it's several pages. And like, for example, the Lagrangian, for example, for classical mechanics, that has two terms in it: kinetic energy and potential energy. This one, it's ridiculously long. Okay, and the math behind it is way outside the scope of this thing in here. So, but if you understand colors, you should be able to understand this one. But please do not take it for actual colors. Okay. Quarks, they really don't have the physical color that we know about, the red, the green, and the blue. But that property now makes sense to use it in the RGB, because when they mix, as if they mix in such a way to form non-color, which is the white color, which is white. Okay, if you take red and add it to green and add it to blue, you get white. So inside a proton, for example, or a neutron, or any one of these particles, you must have colorless particle, meaning one of these quarks, U, for example, and another U in here, and another D in here. So we're talking about proton in here. So if this is red, and this one is green, for example, and this must be actually blue. Okay, and they exchange this color. They don't stay as is. They don't stay as is. How do they interact? Again, we wanted to have a model in here inside the QCD, and those particles are the gluons themselves. So a gluon is both colors. I mean, it has two colors also in it. And it's the exchange of the gluons between these different quarks that makes this interaction possible, that keeps the in this case, a proton intact. Okay, so what's going on in here? This up quark will exchange a red gluon, an anti-blue, it's the same gluon. So remember, you have to have two colors for them. One of them has to be an anti-color, and the other one is a color. So now it lost its red, so it's no longer red, and it's lost its anti-blue, so now it becomes blue. Okay, so whatever color it has, value it has before, it lost the one that has its net value, which was red. And it lost another value, so it's going to lose the entire blue. And when it loses the entire blue, it remains blue now. So that's the only value that it lost. So now it becomes blue. And it's going to exchange it with this quark. Now this quark receives an anti-blue, which combines with its blue and cancels its blue, but also receives a red. So it becomes red. So these two have exchanged colors and now staying together. So that's how the interaction is explained via the colorless also gluon. I'm sorry, this is the not the it's a combination of two colors. Okay, it's red and blue. not red and blue, red and anti-blue. So when you combine red and anti-blue, where are you going to get an or you get a cyan or some other color? Okay, so you get a definite value in here, which is a combination of the two. Okay, so again, that's another value, but it's a definite value in here. Now this one in here that become red, and this one is a green. The one green, for example, can exchange also. It loses its anti-red and loses the green. So when it loses its anti-red and loses its green, first of all, it's no longer green. But then it lost its anti-red, so it becomes red. And this one now gets an anti-red that cancels its red, so it's no longer red. So it becomes actually green. So it's at any given point, I still have RGB. The entire proton still is neutral. But the exchange of these glue ones that are a mixture of two colors, one color and one anti-color, is exactly what needs to happen to glue this entire proton and keep it from flying every which way. Does this make sense? Yes. This exchange of colors is happening. Does it make sense to you guys?
Yep.
Good. I mean, if it really requires some more thinking, maybe you should really, because here is the thing. As long as you ensure, I'm taking in the case of the neutron, you could take the case of the, I mean, I think in the case of a proton, you could take the neutron or take any of those particles, okay? As long as that exchange happens between them in the right colors. I took the simplest interaction between the two quarks. There is actually far more complicated between them. Actually, as the blue one is coming out of one of the quarks, it splits itself, okay, into two more. And then those two will go. So there is the change of color happens in different fashions so that it splits. I mean, instead of going to this one directly, it could go in between and then splits. And this one changes in a different ratio. So the combination of the colors is really complicated fashion. But at the end of the day, no matter what, the neutron or the proton or any one of those baryons stay the same. Now, what's going on inside the meson? It's the same thing. But the meson, remember, is made up of a quark and an anti-quark to begin with. Okay, so it's a quark and anti-quark, and they have to have the same color. I mean, the opposite colors, exactly the opposite color. So for the case of the meson, for example, UD bar, for example. Okay, so you have this two I just took so that would be the pion plus. So this is the pion plus. Okay, so this is a UD bar. Okay, so again, the exchange of the same gluon in this the same. So this one, for example, is green. This must be an anti-green. I'm sorry, anti something else. Yeah, anti-green. So that at the end it's neutral too. But in this case, I could have a particle in here that will take the green and the red bar. So this is my gluon in this case. So this becomes red now. Okay, because it's lost its green, it's no longer a green, and it's lost its anti-red, so it becomes red. But as this one hits this one, the green bar is gone. So it's the entire green is gone because the green and the anti-green, they cancel each other. And the entire red is going to come in here. So the whole now structure of this meson changes in terms of colors. Okay, instead of green, anti-green, now it's red, anti-red. And then this exchange continues between them. So in this case, it's a gluon actually with this property that is keeping this entire meson together. So in trying to understand, trying to come into the physics of this problem, so we hit it with faster and faster moving electrons inside the, for example, the easiest one to do in this case is a neutron. So hit it with extremely fast moving electrons that are coming from the betatron. Remember, you can achieve tremendous speeds with the betatron only when you decide to let go. Okay, because there is no limitation. As long as you can keep on keep on increasing the magnetic field, so there is no limitation. You start from extremely low, and then you increase it and determine the rate at which you're increasing. So that determines actually the velocity, the final velocity with which you're going to come out. So at this point, you have a very fast moving electron, and you put a neutron or even a proton, and it goes way inside of it. So there is nothing that is going to limit it. So at that point, it's going to come and try to break this bondage between them, between these two quarks, trying to isolate a quark, trying to come out with a quark, for example. So what that energy does for you from the electron is going to be so strong that you're going to take that basically gluon and try to stretch it out. And in doing so, yes, one of them will come out, but as it does come out, it's going to leave behind it, because of that energy that came out, another particle, another quark that forms. And the quark that is going to come out in here, the quark that forms in here to replace the one that you took, is going to have an anti-quark with a quark that actually tried to release. And now instead of actually isolating a quark, you ended up with a meson. So quarks can never exist in this universe alone. They have to be always together. That's part of the problem. The least amount of quarks that you can have is 2. You cannot have less than 2. So no matter how powerful your accelerator is, no matter how fast your electrons are moving, and once they hit those targets, at that point, instead of isolating a quark, you're going to end up creating 2 of them, because the energy is so high that leads to the creation of that pair quark anti-quark pair, and then that's a meson. Okay, so that's really what you end up with. So that's the meson that you're going to detect in your cloud chamber or whatever that you're trying to detect your quark with. Okay, it's 9:22. We still have about 3 minutes before the class is over. We are going to come back to this point in here, okay, later on, because at some point in the age of the universe, there were actually quarks floating by themselves. There were the age immediately. So we have the universe went through different kind of time references. The first one is the Planck epoch, and we'll try to understand that. And the second one is when actually quarks formed, and once the quarks and the leptons, basically the electrons and muons and all of them, they were floating freely. But those require tremendous high amount of energies, and that determines that age. After that age basically elapsed, ended, then came the time when they started to fuse, okay? And that basically low enough energies at that point that they cannot be isolated. Quarks did not come out of the picture. Okay, I promise I need to go back into that calculation for the mass of the meson, so I'm going to go through it, and I will communicate with you guys the calculation probably directly via messaging. I'm going to go and post it on the PDF file and send it to you guys. And also, so we're going to finish this chapter on Thursday. We're going to finish all the materials actually on Thursday. So we still have another session when we're going to meet on Tuesday of next week, where we go through some of the problems. And if need be, we're going to meet also the Thursday after. Make sense, everybody?
Makes sense.
Okay,
Professor?
Yes.
For the lab, you posted a copy of lab 9, right?
It's not there?
No, like
Is it missing or what?
There's a double of lab 9, I think.
Okay, hold on. Let me check on it. Actually, that was by design, okay? Use the second version, okay? Use the second version. Okay, one of them is the original instructions. It may be helpful for you to go through it and try to understand what's going on. But the requirement is for the second version, for the web version, which is a shorter version because we're doing it online.
Okay. Okay, and we only have like 2 to 3 weeks left. Are we still doing all the labs?
Yes. We're no, this is basically the last lab. We don't have any. So that's why this Thursday we might actually get into the applications and start talking about the review for the exams.
Okay, so what's the last lab then?
The last lab is this lab, lab 9 that we did last week.
Okay, all right.
Okay, and lab 9, as you mentioned, you have two different instructions on it. One of them says on original, and then the other one says WEB. So I kept both of them to be hopefully helpful for you in doing the lab, trying to understand what's going on in the lab. Although we went a little bit on detail on what to do last time into how to do that lab. Sounds
Okay,
good?
Yeah, that sounds
Okay, very
good.
good.
I had a
Okay.
question on a different lab, if that's okay, or
Okay. Okay, guys, hold on, Natasha, 1 second. The time is done. I know it says 9:26 and we're supposed to end at 9:25. So if you guys choose to leave, that's fine, okay? But if you want to hang around a little more, so that's fine too. Go ahead, Natasha.
let me
Did
just
you-
find it. I think it's on lab, it was on lab 8 we were doing it. Let me check real quickly. So sorry. Oh yeah, lab 8 for table 3. For my values, for my nanometers, I keep getting like really small ones, like things that were like 198
Hold
or
on, hold on.
248.
Let me on the hydrogen atom.
Yeah, on lab 8, table 4.
Okay, let me see if I can get this thing in here to open for me. Table 4. So you have the different values in here. Okay, the easiest way to do, instead of using the electron volt, if you want to, you can keep things in joules. The value in joules is not 13.6. Okay, 13.6 for that calculated value. So if you calculate it correctly with the electron joules, and table 1, 2, 3. Oh, this one for the experiment. Okay. Okay, I think the mistake, and check it again, is the value of x. It might not be x2 minus x1. Try to add them up and see if that's going to help you with this value for lambda.
Okay, I'll try
Okay.
that out. Thank you.
Yeah, try it and see if that's going to make sense to you, because I think, let me try to understand how the rationale behind that calculation is. Try to change the order of this x's and see if it's going to give you a better value for it, okay? Because the simulator, I think, already has taken the two absolute values already in the sum. Because x is supposed to be the distance between them. And if you start from the origin that is past one of them, so it's going to be x2 minus x1. But if you're in the middle, so it's x1 on one side and x2 on the other. Okay, so try that.
Okay, I will. Thanks.
Okay, no problem. Okay. Well, I'm going to end the recording and I will see you guys Thursday.
All right, see you, Professor.
Okay, bye.